Welcome everybody to the last week of the year. So it's week 17. Got Huffman coding due on Wednesday. There are, if you don't know, you're in a group. So make sure you talk to your group members. That is due on Wednesday. All of them are going to be individually turned in. So make sure they're in your directory when you turn them in. I have put some people into mega groups just to see if that will help. So most people are partnered. Some people are in groups of up to 6. So we'll see if that makes a difference. Once when I ran this in the past, students asked me to put into a mega group, and they actually did pretty well. So we'll see. We'll see if that helps. Looks like not too many of you guys did Java Rainfall. Was there a problem with it? I don't think it was super difficult. Java Rainfall. So that's how you do the CN, right? Print some stuff out, make a couple vectors. There is a vector class, by the way, in Java. Array list is considered better, though. So, yeah. So we typically use array list instead of vector 90% of the time. When we get into multi-threading, which I think we will today, there is a difference between array list and vectors, but yeah, in general, that's how you make a vector of integers. So to do input in Java, we just sit there and read one integer at a time. It's similar to my read library. Give me an int, give me an int, give me an int. If they type in a -1, we break out of the loop. If they type in a negative number, we just continue and throw it away. And if the number is greater than 0, we add it to the rainy days vector. And then if it's 0 or positive, we add it to the all data. So we've got 2 different vectors, one for rainy days, one for all days. You don't technically have to do it this way, but I don't know, memory's cheap, so whatever. This is how you can sort in Java. So, that's the C++ way you sort in Java. The collection sort routine is how you sort in Java. So this is going to sort the all days vector and the rainy days vector in reverse order, meaning greatest to smallest. And so that will have all of our data all prepped, ready to go, cleaned up, all that kind of stuff. It prints out the main menu. We grab an integer. If the integer is not between 1 and 5, we quit out of the loop. If they typed in 1, then we print the average daily rainfall. So accumulate is in Java and in C++, accumulate will just add up everything in a vector. And in Java, they did it the proper way, which is you can just pass in a vector to them without having to say all data.begin, comma, all data.end. I wish C++ had done it this way. So you just accumulate, and you pass in a vector. It adds all the numbers up in the vector. Or you could write a for loop to do that if you want. It's your life. You do you. So this adds up all the data in the all data vector divided by the size. There's your average. If there is nothing in it, then you print out no data. And then average rainfall in rainy days, we just do the same thing, except we use the rainy days thing instead. How many days had rain? Just print out the size of the rainy days vector. Max rainfall is the first element of rainy days, because we sorted it, remember? So the first element is going to be the most rain. And then for the other one, we print the top 5 days of rain, and that's the entire program. So that was extra credit, but you know, if you're missing any points and want to pass the class, I would recommend doing it. I don't know. Only about 1 out of 5 students did it, it looks like. So it's not like you can avoid learning Java. Your next assignment's going to be in Java 2. So seems to me like a pretty easy way of picking up points. So I do know that Huffman coding is there, so that's a legitimate excuse, I guess. All right, so 41 chat is still off. Really? Didn't I unlock it? Okay. Weird. Oh, I typed lockdown instead of unlockdown. That's fair. Okay. So I did a switch statement. Yeah, switch is the same in Java as in C++. Is doing function the same way in Java? Yeah. Except it has to be in a class. Okay. So as far as Huffman coding goes, get it done. Yeah. Huffman coding is giving you pain, sure. Yeah. It's normal. If you ever get stuck, please post on Help Center, message me. This is just helping a student before class on it. Yeah, Huffman coding is definitely the hardest assignment this semester. So we will continue our discussion of Java today, and we're going to learn two things today. We're going to learn networking, and we're going to learn multi-threading, both of which are very, very important things. So which one do you guys want to do first? Do you want to learn how to multi-thread or do sockets programming? What do you feel like? Multi-threading allows you to run concurrent threads of execution at the same time. Networking allows you to communicate over the interwebs. Multi-threading it is. Okay. All right. So we'll do it in C++ first, then I'll show you how to do it in Java. What is gold.cc? All right. Then thread.cc. And so in order to do multi-threading, we need to hashtag include thread. And we will be using mutex as well. What are you complaining about? What are you complaining about? Thank you. Go away. All right. Seriously, these things have no chill. All right. So what is a thread? What is a thread? What is a thread? A thread is kind of like a thread is like a separate program inside of a program. It runs at the same time as your other threads. You start off with just one thread, which runs main. Okay, so so what if we wanted to? So a common use for this would be like having one thread handle I/O. So for example, having one thread handle mouse clicks, keyboard inputs, things like that. In fact, with my colors library, it probably would run better if you had a separate thread running the quick read function over and over again, because it only handles mouse inputs when you call quick read. And so if your code is blocking on something else, it won't register mouse inputs. So spinning it off to a different thread would actually probably be a better way of doing it, but either way. So what does it look like? How do you start a thread? Well, there is. Let's see. What's the best way to answer this? Void. Somebody give me a name. I haven't had enough copy to come up with a good name for a function. Give me a function name. So limit how many threads in theory, I guess, but in general, you don't really need much more than the number of cores you have on your CPU. Not foo. All right, so void not foo, and this code here will simply do while true cout 42. Followed by an inline. And then somebody give me another function name. Foo. All right. This one, I guess we can give it a parameter. Just show you guys how that works. While true, cout, whatever number you passed in. Okay, so what we're gonna do is we're gonna have main, and then main is gonna spawn off different threads, and those threads are just gonna run on their own. And the operating system or thread manager, depending on how it's done, will run one of the threads for a while, then it swaps it out and runs another thread for a while, then swaps it out and runs another thread. So we'll technically have 3 threads in just 1 second. So how do we make a thread in C++. If you guys had to make a thread class, what would you call it? If you had to make a thread class, what would you call it in C++? What do you guys think? Thread editor? Yeah, it's just called thread. And so in order to spawn a thread, you have to give it a name. And the name's actually there so that you can see when it ends. So we'll call it thread bob, and we'll pass it not foo. Note, there's no parentheses there, right? You're actually passing a function pointer. So we're passing a function pointer to this object called bob of type thread, and when the constructor on the thread class runs, it actually basically runs this whatever function you pass to it. So it takes a function pointer. It's not a function call. If I put parentheses here, it'd be a function call, and it would call not foo. No, we're passing the function to the. It's like when you pass to sort. You don't put the parentheses there because you're passing the function to sort, and then sort will call that function to sort the vector or whatever. Okay, and then we can also make a thread called simi, passing in foo, and in this case we'll pass in 43. Let's see, no, that's not right. Yeah. And so this will actually do, it'll forward this parameter to the constructor of foo. Okay. So this is going to pass 43 to foo. So both of these get passed to the constructor of Sydney. When Sydney calls foo, it passes 43 to foo. So this is how you can pass parameters to a thread if you want. So we're going to do this, and then we will just say, I'll say bob.join. This means wait for Bob to finish, and Sydney.join for Sydney to finish, and that's it. When you try compiling it, you get a linker error. And the reason for that is because C++ uses what's called the pthread library by default. And so you actually have to pass in pthread as a parameter to get threading to work. Works fine. I sometimes alias that. I guess not. I sometimes alias it. Okay. So if we run it, you can see that this thing runs forever because they're both infinite loops, right? And so it's running a bunch of 42s, and then here's a bunch of 43s. So you can see one of the threads is running for a while, and then it swaps out, and then the other one runs for a while. Then it's scrolling up, scrolling up, scrolling up, scrolling up, scrolling up, scrolling up, scrolling up. There's 42s again. So you can see it doesn't just like print one, and it doesn't just like go back and forth each one. It runs one of them for a while, then it runs the other one for a while, it goes back and forth. So if we want to make this a little more interesting, let's have this actually quit, so it's on infinite loop, for int equals 0, I is less than 1,000, I plus plus. And then it prints all done, because they do finish now, rather than being an infinite loop. So I'm scrolling up, 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 I'm scrolling up. So you can see that the first thread ran first, and probably did all 1,000 of it prior to the second thread running. Okay. So let's make it even more interesting, and let us or if that'll work. I might have to use there's a thread sleep function. Let's sleep for a second. Thank you. So 1,000 times it's going to print 42, then it goes to sleep for a second, and this guy will have go to sleep for 3/4 of a second. Let's make it interesting. There is a threads sleep function that I'll show you guys in a second. Okay, so you can see that the 43s are coming out a little more often than the 42s. Yeah. So let's maybe speed this up even more. Let's make it 10 times faster. So could you include that in the makefile? Yeah. When you make a makefile for these things, so for example, bridges, I believe, needs p threads. So if you go into like bridges heat or something like that. No. But yeah, you'd put it into the makefile, right? So you'd put up here -p thread. Okay, so let's compile, run. So you can see it does 10 43s for every 1 42, right? But it's not. That was interesting. But it's not necessarily. Okay, well, it is exactly 10, but it doesn't have to be. These threads kind of run when they run, and you're not necessarily going to get precisely 10 42s for every 43. Why then is it bouncing from Bob to Cindy in an infinite loop? Should it keep in Bob? Because it is a thread. So Bob runs for a while, then Cindy runs for a while, then Bob runs for a while, and Cindy runs for a while. And these are separate programs, essentially. So a thread is like a different program running within your program. So Bob is a program that's running, and Cindy's a program that's running. They're both running at the same time. They're running concurrently. They're running in parallel. And they're both writing to the output at the same time. Okay. If I were to cut out the end line, remember, inline doesn't just print a new line, it also flushes the output buffer. So if we do that, nothing happens. Let's cut this down to 10. Cut that to 100. So this is going to do, this should run for about 10 seconds. So. Thread is the name of the class. Thread is, it's part of the standard library. So you just make a variable of type thread, you pass it a function, and then that function runs on its own. Okay, so you can see that nothing appeared until the final all done, which is over here, which had the end line. So it didn't flush all that stuff that's being written to until the all done. So all these things are going to the output buffer. And, yeah. Okay. Make it global. Okay, so now foo and not foo are going to be reading and writing to the same variable. And this is something that is rather dangerous. Well, running htop show both threads being used? Sure. If you want, I can up this. But yeah, you'll see maybe both CPUs being used. It's up to the thread manager as to how it schedules it on different CPUs and things like that. But yeah, we can make this 1 million billion. Okay. So it's running background htop. Ah, damn it, it finished already. All right. Session. So we got htop running. CPU's free. We run it. And you see both cores are now being used. Briefly. G++. Might be an optimizer issue. G++. Thread.cc, pthread. So I don't think it, I don't know, maybe it's that fast. Okay, here we go. Both CPUs are pegged now, 100%. So you see, I'm now using both cores on the CPU, and it's as simple as that. If you have a 20 core system, you can spawn off 20 different threads, and so you can see we got a different result with the optimizer turned off. It's undoubtedly overflowing, right? So this is a case where the optimizer is actually going to give us maybe different values, but let's try running it again and find out. It might be the optimizer, but it could be something even more pernicious. So you guys see that? CPU is at 100%. Oh, look, we got a different answer every time. Ooh, that's not good. That's really not good. We're doing 2 billion arithmetics, and we're getting different numbers. This is really not good, guys. This is really not good. Do you guys understand that computers should give you the same output? Right? Like, it's when computers do math, they're supposed to give you the same number every time, and it's not. Welcome to the world of multi-threading. So the most basic form of multi-threading is pretty easy. Like, you just you just spawn off a thread and spawn off a thread, and as long as the two things are like doing their own thing, it's fine. Right? Like, if we were to, have some shared counter here, and shared counter equals 0. Here, this is going to shadow this one, right? And by the way, we don't need to initialize this to 0, right? Because it's a global. Globals are all 0 initialized. If I do this, this will actually shadow this one. And so this thread is actually not going to be writing to the global now. Did you guys know you could do this? If you did this, then if you can have the you can have a variable with the same name in a different scope, and that's fine. You just can't have two things with the same name in the same scope. That violates the one definition rule. But if you do this, it's fine. It's in a nested scope, and so this one is used here when we're reading and writing to shared counter. It's going to be messing with this guy, not this guy. Okay. So if we do this, then it's better to have the same result. Yeah, I agree. All right. So now here we go, pegging the CPUs again. Now we're getting the same number. Why? Well, because this thread here is reading and writing to this variable, and foo down here is reading and writing to this variable. As long as each thread has its own set of variables, it's fine. It's not a big deal, right? So The trouble is, if you are ever going to be reading and writing to the same variable, what's happening is that it's like reading the value here, and then maybe this guy updates it, right? Out from under its nose. And then this guy maybe reads the value, then maybe this guy reads the value, like maybe this guy reads 4, and this guy reads 4, and then this guy writes 5, then this guy writes 5, and so that the extra increment gets lost. It gets lost. And that's problematic. That's really, really problematic, because a plus plus operation is supposed to add 1 to a number, right? It's supposed to add 1 to a number. Or if you have a shared counter plus equals 1,000, it's supposed to add 1,000 to a number. But what if both of these run at the same time? This guy could read the value of shared counter, it might be 5, and then it's supposed to save 1,005 into it. But maybe this guy reads the value of 5, and then this guy runs and he reads the value of 5, and then this guy writes 1,005, and this guy writes 1,005, and one of those additions has now been lost. So that is really bad. It's really, really bad. So yeah, if every thread has its own variable, that's fine. Otherwise, you need to use something called a mutex on it. So let's see here. Mutex, shared counter mutex. Okay, so this is a yes. Okay, so this class here, this stands for mutual exclusion, which means only one thread can own the lock at a time. All right, so let's pull that out. So we're now both reading and writing to the same shared counter, and we'll do this instead. Const lock guard mutex lock shared counter mutex, like that. And if you think I'm reading this from a website, you're absolutely right. All right, and then we do that here as well. And then we're good. Okay, so what happens? What does this do? Well, when this line of code is run, it tries acquiring the lock. Okay. So if somebody else has the lock, it can't acquire it and it'll wait. If nobody has the lock, then it acquires the lock and it will run this code. And when it leaves scope, this variable's destructor releases the lock. So you don't have to manually call lock and unlock, things like that. You just slam this one line of code into it. And basically, as long as everybody who is trying to access the shared counter first acquires the lock on the shared counter mutex, then it should be fine. Okay. See, it's twice the value of the old one, right? And every time we do this, but notice it's only using one CPU now. You guys see that? It's only using one CPU because one of the threads is running, the other thread is waiting for the person to finish. So one thread runs, does all the math, and then when it quits, it releases the lock, and then the other thread picks up the lock, and then it runs. And so basically, we're running parallel threads sequentially here, right? So they take, yeah. So this kind of defeats the entire purpose of a multi-threaded, math thing, right? Because what we really want is to split, because we're doing 2 billion operations right now, right? We got this loop which runs 1 billion times, and this loop which runs 1 billion times. what we really wanted was for two CPUs to cooperate and for one of them to do half the work and the other one to do half the work. But with the mutex here, what's happening is one of the threads, whichever one goes first, it doesn't really matter, acquires the lock, and the other one just sits there and waits. And goes, okay. And then after the first guy finishes, after 4 or 5 seconds, and the second one picks up the lock, and then it runs. And it's safe, but yeah, it's kind of defeats the entire purpose of doing multi-threading, right? And so, better ways of resolving this. You can have them, like I said, you can have each of them have their own variables. You know, that's this is kind of the standard way. Or you can do something like having a vector, you know, where each thread has its own spot in the vector that it reads and writes to. And then after, you guys want to see how to do that? Like, it'll maybe be easier if I just show you. But before I do that, do you guys understand what this line of code here is doing? Do you guys understand this? So as long as all the threads have this line of code in it, then it protects shared counter from being read or written to, it protects that code from running by more than one thread at a time. Okay. So if the function does another thing without a shared counter, it'll just run the other thing until it has the lock. Yeah, it'll run until it hits this line. Okay. And so normally when you use mutexes, you do a small amount of work, right? Like maybe you've done all of your additions, and then you acquire the lock to write the result into it. So if the other thread pauses, if it does not have the lock. Yeah. So if one thread has the lock, the other thread gets to that line right there that's highlighted, and it goes, oh, I gotta wait. It's like a traffic light. And so when there's a cross traffic, I don't know, there's probably some analogy that's better than that. But basically only one person can acquire the lock at a time. And so if this guy runs first, he has the lock and he's sitting there doing a billion operations. Then this guy runs and he gets there, he's like, oh, somebody else has the lock, I'm gonna wait. And he just sits there and waits for this person to finish. When this person finishes, the lock goes out of scope and the destructor releases the lock. Then this guy starts running and it does its billion. Not the best system here, but it's safe, right? So mutexes can really destroy your performance, but let's do something a little more realistic. Let's just add up all of the numbers from 1 to a billion or something. Let's see. So let's do an unsigned integer 64 type. Okay. And so that's fine. Shared counter plus equals I. Okay. So we're going to be doing a billion arithmetics. Okay, so both of them are going to be adding up a lot of numbers. And in fact, let's do this a little differently. So let's say we want to add up all the numbers from 0 to almost 2 billion. We give the first half to the first thread. We give the second half to the second thread. You guys understand? This is a very common thing when we do parallel processing. This is what my master's was in, by the way. So if you have a big task, like adding up 2 billion numbers, maybe isn't that big, but big enough. You oftentimes will split it. You got a big array, you give half the array to one thread, you give half the array to the other thread. Now, secondary characters moving randomly in a game. Yeah, typically AI will run in its own thread. And so the AI will have a thread for each AI in a video game, and it will do things like look around, see if it can see the player. If it can't, it sleeps for a third of a second, and then it wakes up again, looks around, anything going on, no, goes back to sleep. Or maybe it's on a patrol route or something like that. Yeah, typically AI is multi-threaded, and then they just kind of wake up and go to sleep. They don't look like they're going to sleep, they're just walking around, but, oh, bad guy. They pull out their guns and start shooting at them. things like that. Yeah. But I'm more talking like high performance computing right now, right? So if you've got, in fact, we can probably, we'll just go with this for now. We can probably do even more threads than just 2, and I'll probably do that in a second. But do you guys see what I'm trying to do here? I'm trying to add up all the numbers from 0 to almost a billion. Then I'm going to add up the numbers from a billion to almost 2 billion. 1999999999999. Right? Do you guys see that? And so I'm splitting the work across 2 different cores. You guys see that? And because they're both writing into the shared counter, I've got a mutex here. It's the mutex is preventing them from stepping on each other's toes. Okay. So if we go ahead and compile this, let's turn on -03 to optimize it. Okay. And then we'll say time 8 it out. Well, that was fast. Oh, the optimizer, damn it. Optimizer's too smart. It just pre-computed the answer. All right, let's time it. So here we go. Here we go. CPU 1, switch CPU 2. So it takes 6 seconds. Okay. Now, there's the answer. So the optimizer was just the optimizer just pre-computed it. It's like, I know what the answer is going to be. Easy peasy. So now let's see if this would work if the mutex was turned off. Seems like it's taking longer this time. Wow. Yeah, okay. 12 seconds instead. And it gave us completely wrong data. The reason for that, you'll probably have to take CSI 45 to understand caching and things like that. They're probably thrashing each other's caches. So, what if, instead of doing that, we had 2 shared counters? Shared counter 2. And then down here in main, we say shared counter plus equals shared counter 2. So just each guy computes their own sum, and then at the end we combine them together. So give us the correct answer this time, right? Interesting, though, that it's not any faster. Interesting. How would you not be faster? Yeah, with the mutex, it's essentially turning into single-threaded mode. So I think what it's telling us is that single-threaded is actually faster than multi-threaded on this. Let's try this. 1 to 2 billion, and we just won't run Sydney at all. Let's see how fast this would be in single-threaded. Yeah, so essentially the single-threaded performance is actually better than the multi-threaded performance on this system. It's interesting. My server, as you can see, is not very powerful. And so it's only got 2 cores. And so it's possible that we're getting some cache contention when 2 of them are running at the same time. So they might be in the same cache line. And so the L3 cache might be having to work hard. So let's see if we can do this instead. sum equals 0. So do you guys see what I did here? I moved the lock guard down so that rather than having to have the lock guard waiting while you're doing all of the arithmetic, I moved the lock guard just to when we're updating the shared variable. You guys see the difference here? So what this will do is it'll allow this billion math operations to take place, this billion math operations to take place. They each have their own stack allocated variable. Each thread has its own stack, by the way. Not a lot of stack memory, but enough. And then after we've computed the sum, then we acquire the lock, slap the sum into the shared counter, and then it goes away. And this is how a mutex should look. You shouldn't have a mutex and then do a giant computation. A mutex should be protecting just a real short operation. Otherwise, your performance tanks. Let's put Cine back in and see how this goes. And part of the problem here is also the optimizer isn't running. So you can't really trust any timing values you get. There you go. So getting a different number now. Did I type in? Oh, it's because it's an int. So we're going to have to modify this in a second so that we can fool the optimizer a little bit. Let's see if we can get some better timing data. There you go. So we're now beating the single-threaded performance slightly. A little bit. You can see the CPU utilization has gone up from 99% to 195%. So we're getting close to we're getting very close to actually using the both cores at full volume. You know, there's only 5% more performance we could squeeze out of the two cores. So not bad at all. Not bad at all. So lock guard should be used right before writing to variables. Yeah, that's yeah. You want to have as little of your code locked as possible. There's also something called atomics, which is an even maybe easier way of doing that. Let's see. Support. Let's see, CPU reference. So threads, very useful stuff. Like I said, you'd spawn off different threads to do work at the same time. Mutual exclusion is used to protect anything that's shared between threads. And then there's atomic things which allow you to have lockless. A lock is another word for a mutex, kind of. Lockless concurrent programming. So you can read and write to variables without getting those issues of them stepping on each other's feet. They're free of data races. A data race is when two threads are reading and writing at the same time, and you get different answers, which is really quite scary. So let's see if we can find some sample code here. Atomic int, atomic uint 64. And this is in the atomic header, I believe. Yeah, okay. Remember, atoms can't be split. So make you an atomic UN64T. Then all right, you can't use plus equals. You get what get fetch add, I think it's called. Fetch add. Okay, that is the right one then. Okay. We will add in sum, and we will say, what was it? Relaxed. Stood memory order relaxed. So the atomic library allows you to do essentially these two things here without actually needing a lock. And so if you have a lot of threads all reading and writing to the same thing at the same time, and they're just adding to it, because additive is cumulative and associative and all that stuff, and it doesn't really matter what order they go in, you can get. Ooh, it didn't like that. Yeah, so the performance is about the same, and the reason why it's about the same, we squeeze another 2% out of the CPU, maybe, could be a rounding error. Even better, I guess. It's because our mutex wasn't. This is actually fine. Like that's not going to really hurt your performance too much, because we did a big computation at the end. We just acquired a lock really fast, wrote to a variable, released the lock. It's not a big deal. There is a better way though, which is using atomics. So atomic variables, you can there's certain operations you can do on them that you don't have to have a lock on them. It'll just say plus equals, and it goes. So yeah. So it's a way of doing arithmetic without needing to go through having a mutex and acquiring a lock, doing the operation, releasing the lock. So it is a little bit faster. Okay. What is memory order relaxed? There's different options for it, and in this case, that's the right one. We don't care if one thread goes before another thread. It's all good. Okay. You guys have any questions about this? We use threads a lot in CS45. 45, we talk a lot about the memory subsystem, and so understanding why things are the way they are, and how to squeeze more performance out of systems and things like that. Yeah, it's more what I was getting out with that. Parallel processing is more of a junior level topic. I'm starting to bring more and more of it down, though, into the freshman and sophomore levels, though. Because you can see it's not super hard. Like, you just, just make a thread and pass what function run, and it runs in its own time. And then you call join on it, and that means wait until Bob finishes, wait until Sydney finishes. And that's it. It's not that gnarly, I think. Yeah, if you have a giant array, like your typical usage for multi-threading is like image processing, video processing, things like that. So if you've got 20 cores, like a Threadripper, and you're going to be running the same image filter on every pixel on the image, what you can do is you can break the image up into 20 either strips of rectangles or squares or something like that. There's different ways you can divide a problem up, but basically you can divide it up into 20 chunks. You hand each chunk off to a different thread, and then each thread read and writes to its own chunk of memory, and in theory you'll get close to 20 times the performance. Sometimes you'll get more than 20 times the performance, depending, and which doesn't seem possible. How do you get more than 20 times the performance with 20 threads? Well, take CSI 45. If your code will fit into cache better, then it will. You can get what's called superlinear speed up, and I've done it before in my own code. It's a nice feeling. So let me show you that, I guess, and then I'll move on to networking. No, actually, I want to get on to networking. Yeah, basically what you could do is something like this. Int pointer array, size t start, size t end. Oops. And so we are going to say for int I equals, let's make it a size t now. So if we have a giant array, and we want to add up all the elements in it, we can make this function here. Let's give it something descriptive. Array sum. Don't do anymore. So you do something like this, and threads equals read. How many threads do you want to spawn? And then int size t size. How big an array do you want? Okay, so let's say the user say, I want 20 threads and I want an array of size 1,000,000 or something like that. So what you can do is then say int array equals new int square bracket size. We'll remember to delete it later, like that. So we make a giant chunk of data, and we could say we do generate or generate. Do I have that? Okay. Well, R to R plus size, passing in rand modulus 100. Nope, no, that won't work. lambda time. So this here is a function. It's an anonymous function. And so what that's going to do, it's going to fill the array with numbers from 0 to 99. So this is a lambda. And so that is a function with no name. I'm passing that in as a function pointer to generate. Generate will call that function on every element in R from the beginning to the end. And if we see out for int I equals 0, I is less than size, I plus plus. See out R, let's go back to I, verify that works, G plus plus. How many threads? 10, we're not doing anything yet. How big an array? 10. So there we go. So we were generating 10 random numbers. Have you guys seen this before, lambdas? Some people love lambdas, and so they don't like making functions if they can avoid it. So that syntax there is this. This is a function with no name, no return type, and no parameters. I need to take this, sorry. Pause the recording real fast. Okay, so yeah, this is a lambda. We talked about it when we were going over the standard library. I could have made a function that did this. I could have been like, yo, int my fun return rand modulus 100, and down here, rather than doing a lambda, I could have done my fun like that. So this line of code here and this line of code here is the same. Generate, again, is a standard library routine that takes a beginning point of a range and ending point of a range and calls this function you pass to it, myFun, and the result of that gets put into every spot in that range. Very simple way of generating random data. A lot of people, though, don't like polluting the global namespace, and so rather than making a function called myFun that's only used once down here, they will use what's called a lambda. And so a lambda is a function that has no name. It doesn't exist after this point, so it can't be called again. But it gets passed to generate, and generate will call this function over and over again and use it to generate a random thing, and then the function vanishes. So a lot of people like writing code like that. I'm sort of neutral on it. All right, so, and then what we do is make an array of threads, and for each thread, we would pass it a chunk of the array to do. However, I do want to get onto networking. So we'll just pause this here and maybe pick it up later. So this is, do you guys kind of understand, though, how threads work? You just say, like, thread, you know, whatever. And then it just runs whatever function you tell it to run. And it runs on its own time in its own place. Okay. It's not too bad, I don't think. The hard thing about multi-threading is when you're doing things that are not thread safe, like reading and writing to a variable that's shared between threads, then all sorts of horrible things happen. You accidentally open up a gateway to hell, and demons start pouring out. Like it gets really bad. But that's why the good Lord invented LockGuard, right? And so, or atomics, right? So, if you need to have multiple threads reading and writing to the same global or something like that, then you use LockGuard and just protect it with a LockGuard. Or if it's amenable to atomics, you can use atomics. There's different math operations you can do that don't require a lock. It just does a plus equals without splitting the operation into multiple commands. Okay, get Doom guy in on this. Yeah, exactly. So yeah, threads are really, really useful, and it's in fact one of the, here we go, Doom guy on the chat. There we go. So if you know how to do multi-threading, you're going to be a very employable programmer. Let's put it that way. when I majored when I specialized, I should say, in high performance computing, the only people that knew how to do multi-threaded code were people that had taken parallel processing. Some people were self-educated on it, but yeah, if you didn't do it right, it would hang, it would freeze. You'd run your code and you get different output. It was really bad. A friend of mine made a lock-free logger for Microsoft, and he came in and demoed it, and I found a bug in it. So it's really hard. If you, I don't know. So I don't think it's that hard, but like if you haven't, I don't know, been trained in it, it's hard. I don't know. It's one of those weird things. But the way that history has been moving is that for years CPUs got faster and faster in terms of clock rate. So you'd have 100 megahertz one year, you'd have a 200 megahertz the next year, and a 400 megahertz the next year, and every 18 months the clock speed on a chip would double, right? And nowadays it's basically stagnated since about 2010. Since about 2010, we've only had incremental gains in clock speed. Almost all of the gains in processor power has been through having more and more cores, having more and more CPUs within a CPU, so to speak. So you see the server here has two cores on it, but like my home PC has more. It's got 5 times 4. It's got 20 different cores, or it's got 10 cores. It's got 20 logical cores. So it appears to be a 20 CPU system. In reality, it's a 10 CPU system, 10 CPUs within a CPU, so to speak, 10 different cores. And so my CPU would be able to run 10 threads concurrently at full power, and so it would be 10 times more powerful than a normal 4 gigahertz CPU. Right? In order to program that, though, you have to understand threading. So there's lots of different ways of doing it. I think that approach is pretty reasonable. And so if you know how to do it, most people don't, then you're employable. So supply and demand. Everybody needs multi-threaded code these days because that's the direction CPUs have been going in, and very few people know how to do it. Or, not very few, but like it's fairly rare. There's a lot more people that know how to do JavaScript and Python than know how to multi-thread code. Okay. So our next topic is sudo deploy homework, csci 41. Sockets. Okay. So what we have here is, what do we have here? Remove client, remove server, g++-o client, .cc. That's funny. Yeah, put a comment there, I guess. Could we have used multi-threading to make the probing, chaining, benchmarking assignment take less time? Yeah, absolutely. Sure. The server, like you can see, like it's not super powerful. Like even when we multi-threaded it, like it's not any more powerful. It could just actually be one core that's pretending to be 2 cores. It certainly does not seem to be very good. On your own machine, yeah, you could see easily a 10 times speed up. How much computing time the server takes to deploy the homework? Student Flores right now. Yeah. Okay. So let's talk about sockets. Okay. So you know what? I'm gonna figure that out. Okay. So let's take a look at the Java version of it first, because actually Java is a little bit easier to understand than the C++ version. So let's start with the server. So the Echo server, Java compile, echo server.java. Java compile echo client.java. Okay, so if we java echo server, and we'll choose port 9000. So that guy's running there. Snap it over to the right, quit, and then to sockets. Java echo client. And so we will run it on localhost connected to port 9000. Hi, and then it bounces back hi, bye, sends it over here, sends it back, bye. There you go. It's the world's most boring internet application. But that's usually what we start with. Whenever we do internet application development, we usually start with just a chat client where you can just send a thing to a server and then it bounces it back to you. Or if multiple people are connected, then they can all chat with each other and things like that. So how does it work? And this is super basic, maybe almost too basic. Let's snap this up here. Okay, so this is an entire internet server right here. It fits on one page. Okay, and this was taken from, I think, the Java documentation. Could be wrong. And so what we have here is main, right? Main takes an array of parameters, takes a command line parameter, and if you didn't type in the right number of command line parameters, then it gives you a usage where it says run this by typing Java echo server port number. So how the internet works is that anytime you have an internet service, you've got a host and you've got a port on that host you connect to. So for example, if you connected to the localhost my server on port 80 or 8080, that'd be the web service, right? There's designated port numbers for different services like FTP and SSH and things like that. I ran the server on port 9000, so I just picked a number at random, and then what happens is we parse the command line parameter. This is how you go from string to integer, by the way. So that's a string. Args is a string. And so it's the string double quote 9000. This turns this into the integer 9000. And then that is how you make a socket. So a socket is, it's called that because it's like how the power company works, right? You don't have to worry about how electricity gets to your power socket, right? Unless it doesn't work. And then you start debugging. But like, you basically have a socket that looks like this, right? You know what I mean? You've got a plug. You plug the plug into the socket, and you've got like your lamp or something. And you got a light bulb in there, and light turns on. And so you actually don't know how does power get here, right? Is your electricity coming from a local hydroelectric plant? Is it coming from rooftop solar? Is it coming from some a natural gas place? You don't know. All you know is you plug your thing into the socket, and it just works. That's how internet sockets work. So internet sockets, you've got the server, and the server is going to have, like I said, this is port 9000. And so the server can put data into here. And then when a client connects on port 9000, that data comes out. You have no idea what's happening in between. And the client could put data into the socket, and the server will read that data back out. And so the client can put data into the socket, and then the server reads that data. The server can put data into that socket, and the client reads the data. Do you guys understand? So you just basically read and write to this thing, and it's magic how it works. You can take a networking class, which I highly recommend, to get details on the 7-layer burrito model of how networking works. But for all intents and purposes, if you've got an internet connection, you don't need to worry about it. If your internet's working, it's good enough. And that's all I really need to explain conceptually. So this creates a new server socket on port 9000. and then it'll sit there and wait. Accept means just wait until somebody connects to the server. So it'll just sit there and wait until somebody connects. When it connects, it creates a new socket. And the socket has a input stream and an output stream. This is like C in and C out, right? And so that's the output stream, that's the input stream. It's like C in and C out, except it's over the internet. It's over the internet. And then you can just read to it and write to it, just like you read and write to standard in, standard out. And data will just go across the network. It's all magic. Okay. And so all the server does here is it just reads a line from the internet, and then it writes it right back out. And so if I wanted to, I could be like out.println. You guys see how this is the same, right? It's the same, like we had print and println with system.out. Right? In fact, I can echo this to the screen if I wanted. Out.println. Kearney says hi. And so that'll write Kearney says hi to the socket. Out is the output stream. It's the socket. You just write into it, you know. And there's different classes: print writer and buffered reader, input stream reader. You notice how it's like new buffered reader, Passian, new input stream reader, Passian, client socket.get input stream. Remember how I said that Java was verbose? Java is verbose. Java is a very typey language. They like typing. They like wearing out keyboards in Java. So the net effect of all this is that you've got this out thing that you can write to, and it just goes over the internet, and this in thing you can read from, and you can just read things from it over the internet, and that's it. It's magic. And if we wanted, we can do like system.out.println and be like red plus input line. That should work. And so now the server will print to the screen when it gets something from a client, which makes the server a little more interesting to look at. Okay. So let's javac echo server.java and run echo server java echo server again on port 9000. Snap it over. The client's still the same. Java echo client. Localhost. Localhost just means the machine you're on. And I'm going to connect on port 9000. So I connect here and go hi. And so see how it's printing to the screen now? Printed hi. And then it echoes back. Kearney says hi. Oh, but it only read once, right? Because I sent two things over. The client we're going to have to modify as well. The client only read one line. It should be reading two now. So if I were to type something else, it's going to get the last. Do you see that? So it sent a string over the internet, and the client read a string. And then when it read the second string, rather than getting DSDF or Kearney says hi, it gets what was in the queue. And so if we type in something here, see how it's like running further and further behind, right? It's because the client's only reading one string instead of two. So okay. And then the server quits when the client disconnects. So when the client disconnects, when the client disconnects, it gives you a null. When you call it read line, it gives you null, and then it just terminates the program. In reality, you probably wouldn't have a server that quits after one person quit. So we're going to have to modify the client, echo client.java, snap that up. And you can see on the client side, it's very, very similar. In fact, it's almost identical. It needs a host name because it needs to know which host to connect to. Google, localhost, whatever. So you're going to pass an echo client, localhost, port 9000. That's how you quit, exit, same name. Is that how SYN flooding works? You plug into all the sockets. Now, SYN flooding is It's when you connect to a port and you initiate what's called the TCP handshake, where you send a SYN and they send back an ACK and you send back an ACK, and then that completes the connection. With a SYN flood, you send a SYN to it, and it writes back an ACK, and then you just don't do anything. And what happened was the Linux kernel originally just had a giant array of all the incoming connections that are half open, and it just had an order in operation on them where it would just scan over them. And so if you flooded it with SYNs, it would fill this buffer up all the way. It would drop connections, and it became very slow because it was doing an order in lookup when it shouldn't be. It should have been order login. And so they had to redo the Linux kernel to harden it against those kinds of attacks. Okay. So it's no more than a normal DDoS attack nowadays. Okay, so good question. So again, all this is the same. New socket. There you go. So in Java, there's a socket class, and you pass in a host name and a port number, and it connects to that. Connects over the internet. That's it. Pretty easy, huh? What do you guys think? If you're going to connect to somebody on the internet, new socket. www.google.com, port 80. You've now connected to Google's web server. That's it. So host name's a string, port number's an int. And then this sets up the input and the output things. Like I said, this is the Java verbosity. Buffered reader n equals new buffered reader, new input stream reader, echo socket, okay, input stream. Right? Java loves what are called decoration code patterns, where you pass a class to a class to a class, and each thing you pass it to adds something to it. Like buffered reader improves the performance of a read by having like an input buffer, things like that, or output buffer. Well, reader is an input buffer, obviously. And so this does the same thing for the keyboard. This is standard in, right? And so it turns the keyboard into a buffered reader to improve the performance. And so it will read a line from the keyboard, standard input. It reads a line from the keyboard, and once you hit Control D to close the thing, it gives you a null, the thing quits. It then writes the string that you write from the keyboard to the internet. That's it. Out. Dot print line. That just pushes the string over the internet. That's it. That's how easy it is. It's like if you can do CN and C out to the screen, you can do CN and C out over the internet, right? It takes an extra line of code. You know, who am I going to connect to? That guy. All right. You know, and then you set up your ability to write to it and read from it. You know, so you just say out.println, and you just print to the internet, and it goes to the server. And then we get one line back, and so we need to change this to read 2 lines. Java echo client Java. Oh, couldn't connect because the server is not running. So Echo server is now running on port 9000. We connect to port 9000 in the local machine. Hi, and now we read 2 strings. The first string is Kearney says hi, and then it echoes back the string that we sent it. There you go. If you can do that, you can do anything. Where do you get the port number from? I just made it up. So when I ran the server, I typed in port 9000. I didn't have to. I could have typed in 10,000 or 4321. The only thing you can't do is you cannot run it on a port below 1024. So if you try running Echo server on port 9, it doesn't work. Okay. Port 10 doesn't work. Okay. All the ports below 1024 All the ports below 1024 are protected by the system. You have to have root access to open a port below 1024. So just pick a number above 1024. 1024 and up, you're good. Okay. Now, if I'm running on port 9000, you can't open port 9000. That's actually really important here too. So like if I'm running the Echo server on port 9000, if you guys try it right now, it'll be like, sorry, ports in use, can't do it. So pick a different one. Was this language built with internet connectivity in mind, or did it just come along? So Java came out in like 96 or 97, and that was when the internet was like becoming a thing. So it's had sockets in it since the beginning. And C++ sockets are gnarly. They're not nearly as fun. Like, you can see how easy it is in Java. When was the first release? 95, okay. Yeah. So, yeah. And so, that's all it is, you know. That's it. Connect to a host, www.google.com, www.microsoft.com, whatever. You give it a host name and a port, and then it tries connecting to it. If it can't, it quits. If it does connect, it connects, and then you can send and receive data just like you're CNing and C-outing. It's pretty easy. What machine is the Echo server? It's this machine. So localhost means the current machine you're on. Another way you can do that is, let's see, Java Echo client rather than localhost. You can type in 127.0.0.1, and that's the same thing as localhost. So if you don't know the IP address of the machine you're on, you just type localhost, or you type 127.0.0.1, and it connects. You can run ifconfig and do it that way if you want. So you can give the actual IP address if you want. That's kind of a waste of time though. 127.0.0.1. Not 120, 127. Yeah. Me and Java have the same birthday, just 7 years apart. Nice, nice. So the client is connecting to its own machine. Yeah, sure. Yeah, sockets work over the internet or they work locally. It doesn't matter. In fact, if I need two processes to talk to each other, this is a different way of doing multi-threading, right? It's not exact. I mean, you wouldn't call it multi-threading in that case. It's because they're two separate processes. But yeah, if you need to do multi-threading in a little bit more heavyweight fashion, you want to have a separate client and a separate server. You don't want one process running both of them, which would be kind of weird sometimes. Like if you're making, you know, some physics engine that's doing a big simulation, and people all over the world can participate in it. You run the server. And then people can connect to the server, and the server can feed them data, and they do the computation, and they send you back the result. But you can run it locally on the same machine if you want. In fact, that's usually how I test my stuff. So I run the server on my local machine, and I just have multiple clients on the local machine connect to it, and it works fine. You can. It doesn't have to go over the internet. But when you do sockets, it can go over the internet. So if you were to run this program here, like if you were to download echoclient.java, if you were to download that onto your PC or Mac at home and typed in the IP address for the server, port 9000, it would connect. It would connect to my server here. It would work fine. So it's the same way you can pass data locally between two processes on the same machine, or you can run it over the internet, and it's as easy as C in and C out. So the C++ code is not nearly as fun. It's really not. If you look at this, right, that means internet, because the sockets library is back before the internet was called the internet. Exactly. It was called ARPANET. And so ARPA, the Advanced Research Projects Agency, developed the internet as a way of having a nuclear bomb-proof network. And so that's where the internet came from. The internet came from the military, and the military wanted to have the ability to communicate even if the Russians dropped nukes all over our country. So that's why you hashtag include ARPA/inet.h. Why you have to specify, I want internet, because this is back before the internet was actually the standard. In Java, you just do socket. Yeah. So, yeah, and you create a struct sockadder in, and you set options on it, and you say the socket family is for internet, and the port is 8080, and inet p2n af inet 127 server address. Yeah, it's way more gnarly looking than Java, which is one of the reasons why I teach Java. It's not only to make you guys employable, but because it's the networking is a lot easier to do as well. So this is how you send data. Send. At the end of the day, it's not too bad. Over the socket, here's the string. Here's how long the string is. Right, because this is C. That's not C++, it's C. Sends it and then reads from the socket into the buffer a maximum of 1024 bytes. That's how many bytes are read, and then it prints the string that was read back. That's basically the same code. It's just as... I think it's Cold War for the internet. Yeah. Yeah. I mean, you know, there's always unexpected consequences, you know, and so all of these, you know, cat memes and all these things, they all developed from people in the military being afraid that their point-to-point communications would be cut. And they wanted to have a networking system that could go around damage, things like that. So that's where the internet comes from. So that's it for today, guys. We will pick it up on Wednesday. Get Huffman coding done. It's 20 points. It's a huge chunk of your grade. Don't just punt on it. Don't just ignore it. Get it done. All right. There's a lot of starter code and hints. It is hard though. So ask good questions. Okay. That's it for today, guys. Good luck.